We want to introduce what the idea of optimal control is, how it is different from conventional optimization, and yet the ideas that you learn during a course in optimization still turn out to be very, very handy. Okay, so this being the introductory lecture, although I have posted this on Moodle, I'd like to again mention the main textbook for this course. It's going to be the following: Optimal Control Theory, a concise introduction. This is by Libazon. Okay, that's the book we'll be referring to for most of the theory. Okay, however, you also need to solve a lot of problems for this course. It's a mathematical course, there's no bypassing that. So you'll also have this book. It's a pretty old book. By Kirk. Okay, so this primarily for solving problems, this one mainly for following up on the theory that we cover in this particular course. Okay, so get hold of these books. I'm sure you'll find copies in the library or otherwise. You can also think of procuring. I think this one, a preliminary version, is available freely online, shared by the author himself. So you don't have to break any legal barriers to get hold of this. Okay. Anybody else care to volunteer? Maybe a third voice? I've heard two of you. One from economics, one from electrical engineering. What brings you here to this course? You heard from friends, okay, word of mouth. Okay, not a very sound technical reason, but good reason, I should say. All right, so what is it that we do here in this course? What kind of goals should we set for ourselves in this course? As I said, we're going to deal with dynamical systems here, right? What do we mean by dynamical systems? Dynamical systems that are given by differential equations, to be precise, ordinary differential equations, okay, which look something like this. Sorry. Yeah. Can you tell me what those symbols mean? What is x, what is t, what is u, what is x naught, what is t naught? What are these things? Anyone? Sorry? X is state, very good. So x, it's an n tuple. I hope you're familiar with this notation, right? It's an n tuple. So there are n states. What are states? Can anybody tell me what are states? You've all done a course on control systems. How do you define states? I'm not asking for the choice of states. So don't give me an example of a state in a particular electrical circuit or a mechanical system. What are states? Anybody remember? Yes? Don't be afraid to be wrong or incomplete in your answer. That's how we all learn. Yes? What is a state? Well, a lot of things change with time. In fact, in this particular expression or equation that I've written here, although I've not made it very explicit, this x and u are also functions of time. Yeah, we might not have mentioned them very explicitly here, we might have suppressed them here, but they're also functions of time. So is u also a state? Because it changes with time. What is the utility of states? Why do we need states? How do states help? What is this? This object here. At the heart of it, mathematically, what is this object, mathematically speaking? It's a differential equation. Fantastic. What is this? Initial condition. So even without being told, you know that T naught is the initial instant and X naught is the value at that initial instant of the states. Very good. So what would we like to do with this bit of information here? Typically, if I give you a differential equation and an initial condition, what do you want to do ideally? So you would want to solve this, isn't it? It's an IVP, an initial value problem that you would like to solve. Of course, unfortunately, a vast majority, in fact most of the differential equations are not analytically solvable in closed form, which is why you resort to something such as qualitative analysis and try to figure out at least how does this behave in the long run. As time evolves, how do these states evolve? Yeah, that brings us to questions about stability or about confining the states to certain regions. Yeah, so that is the utility of states. They are the minimum bit of information that allows you to extend the solution. Given the information about the states at some instant, say T naught, you don't really care about how they came about to that point, rather you just keep propagating the solution thereafter ahead of it. That's what you would ideally like to do with the states, right? So given the state information at this instant T naught, you would wish to propagate the solution into the future for T greater than T naught. Sometimes you also write this as 0, yeah, but in this course we'll stick to T naught as the initial instant. Okay, it's just a choice of reference frame in the time scale, nothing else. Okay, so this is a differential equation. The course says optimal control. So this is just, okay, you can see some tenuous connection with control in the writing of this differential equation. Where does optimality come in here? What makes this optimal, perhaps? Yeah, what do you think? How do you optimize something? If I give you a function, say x squared, between -2 and 2, what's the minimum of that function? 0. How do you get to that minimum? By choosing what variable? No, that's the method for getting to it. By choosing which variable do you get to arrive at that minimum value 0? Which is x, the independent variable. Yeah, okay. In this case, in a control system, what is it that you can choose in order to make it behave in a certain way, perhaps in an quote unquote optimal way? The input, so the control, the u. Yeah, so this is the variable that you shall be playing around with. Yeah, okay. Where does this u come from? Well, in a typical multivariable system, you would say that u belongs to some set of admissible controls. Not all possible controls can be admissible, right? Which is contained inside an M tuple. So there are M inputs, okay, in general. We're not considering just a single input, single output system. There are possibly M inputs. Within this M dimensional Euclidean space, you could have the entirety of this, in which case your control is unconstrained. Or you could have a constrained set within which you can choose your controls from. So at every time instant t, you get an M tuple, yeah, which belongs to this set U. This could be an ellipse, this could be a hypercube, it could have all sorts of different kinds of shapes, doesn't matter, but the point is that this is where this fellow lives, this is where this fellow lives. So of course x dot also lives inside the n tuple. Time is the most independent variable, something you cannot control, it flows on, right? Okay, but that still doesn't answer our question as to Where does the optimality come in here? Okay, there's nothing optimal about this. Like I said a while back, fx is equal to x squared, and you know how to minimize it. You differentiate it, as one of you said, and you equate it to 0. Yeah, and you say x is equal to 0 is the point of optimality, and at that point of optimality the value of the function is also 0. Here, what indeed is my function that I am trying to optimize? Is it f? Doesn't make sense. So what is being optimized here? We need to define that. How do we do that? So we say that this is how we define the j. I'll clarify the notation shortly. This is L, as you shall later on learn to call this the Lagrangian. Once again, I am suppressing the dependency of x and u on t. It is implicit that both x and u also depend on t. Okay, what is the significance of something such as this? Let's try to wrap our head around this. This was familiar. This may not seem so familiar. But our subsequent discussions will reveal that this is actually the most natural way of choosing a so-called cost or a cost functional. What's a functional? If you've done a course on linear algebra, you might have already encountered linear functionals. Spaces, vector spaces, dual spaces. Doesn't matter if you haven't, don't worry, don't get bogged down by the names. What's a functional? Well, it picks out a vector and spits out a scalar. Why is this a functional? Where's the vector? Okay, you can imagine that T naught is a number, Tf is a number, so the result of this integration is number. This is also a number, fine. So it spits out a scalar. What's the vector? Can anybody tell me what's the vector here? Is it u? Which is it? Both x and u? But really, what is it that you just told me you had chosen here in this? Wasn't it u? In fact, that's also the reason we shall write this as a function of u. Depending on what u you have chosen, your x will propagate accordingly. It's not like you are controlling x independently. It's very important to understand this difference right at the beginning. Yeah, because later on we shall very shortly delve into calculus of variations where we will not have an explicit control, and again just prior to mid-sem we'll probably get back into this optimal control framework where we'll bring this u back into reckoning. You see, we are only choosing this u, we are not choosing the x. We cannot access x directly, we can only change x according to our desire through this handle that is u. Yeah, so this is actually going to be dependent on the choice of you. You choose a certain control, your friend chooses a certain control, both of you end up spitting out two different values of this function null. So what's the vector here? The vector is basically an m tuple of functions. That's not a very usual kind of vector that you're most familiar with perhaps. Most of you have familiarity with vector spaces that look like Euclidean spaces, which are at the end of the day a very, very crucial property, finite dimensional. You may not be able to draw them beyond n is equal to 2. Some of you might try to draw it for n is equal to 3, including myself. But beyond n is equal to 3, you cannot draw them. But still, if n is a finite number, you have a rough idea about what it looks like, what it feels like, what are hyperplanes in that Euclidean space. Unfortunately, when you deal with spaces of functions, those do not look like these finite dimensional vector spaces. There are differences, and yet there are also similarities. Okay? So, we shall try to glean as much insight about the optimization problem based on our understanding of finite dimensional vector spaces and see how much of it still carries over to the case of infinite dimensional vector spaces, which are function spaces. Yeah, and then we shall try to see where the similarities are, where the differences are. So which ideas of conventional optimization can be pushed through and where we actually hit a stumbling block. Yeah. Let's discuss a few examples of problems that could perhaps be represented in this manner. Yeah, so you would typically have something that looks like this: u1, u2 dot 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 till um, and these are all functions of time. Even if, and I want you to be absolutely clear on this, even if m is 1, even if this is a single input, the space of functions is still infinite dimensional. Yeah. Why that is so? It would bring us to the question of what indeed is the dimension of a vector space. What's the dimension of a vector space? The size, the cardinality of its basis. If you have function spaces, I mean, the easiest way to convince you about this fact is think of periodic functions. You're all familiar with the Fourier series. Yeah, how many terms are there in the Fourier series? You can truncate them, but by truncating them, you will be having some error. If you really want the full glory of the function recreated, you'll need infinite number of terms. In fact, those are a very special orthogonal basis. Again, I'm just throwing in some terms here, don't get bogged down by them. We'll get to them. Not maybe functional analysis per se, but at least what I'm trying to convince you of here is that the space of functions, irrespective of this m, don't look at this m and think of this as a finite dimensional vector space or an object in a finite dimensional vector space. The moment this becomes a function, it is infinite dimensional. No questions asked. Yeah. So in fact, this kind of a problem, if we try to solve, we are essentially trying to solve a dynamic optimization problem over infinite dimensional vector space, which is a function space. In fact, you might be further restricted because you might not have access to all possible functions. Depending on this choice of u here, I might want some nice kind of a control, right? You might say, oh, okay, look, I have solved the problem. I have given a control signal, but maybe that control isn't permissible. Think about, for instance, digital systems, which only allow you to take values, say 0, 1, 2 or things like that. And you give me a function which spits out values such as 1.414. It's not implementable, right? So depending on the set of constrained control, you'll have to choose the best possible control, okay? Already I have touched upon a very, very serious issue here, an issue that plagues all of calculus. What is it? You need a certain kind of a smoothness, yeah? So if I ask you to optimize over a set of control inputs, that may not have that requisite kind of smoothness. Most of the methods that rely on calculus will falter. If you want to see a very straightforward example of this in the domain of static optimization, think about mod x. If you want to find out the minimum of mod x, would you go ahead and differentiate it? That would be silly, right? You can't differentiate it at 0, and yet you know from the sketch of mod x that at x is equal to 0, it attains its minimum. You know it because you have an idea about what it looks like, but you don't differentiate this. So calculus per se, the differentiation, the good old techniques of differentiation no longer are handy. Yeah. Same thing happens, something very similar happens when you're given some weird kind of constraint sets or control inputs where differentiation or calculus tools may not be very handy. And yet we shall see that throughout this course we shall be aiming towards developing certain tools that will enable us to solve even such problems where calculus may not be very handy. Yeah, which is the celebrated Pontryagin's maximum principle, the PMP. So a good amount of time in this course will be dedicated towards a proof of the same, Pontryagin's maximum principle. This course will take you on a journey over a course of say 400 years or maybe even thousands of years, one might say. Some of the problems that we shall talk about, they have a great deal of history involved with them. But PMP, on the other hand, is barely 60 to 70 years old. So you will be literally, as Isaac Newton said, walking on the shoulders of giants who have visited this domain, from Euler to Lagrange, yeah, to Bernoulli, to Isaac Newton, right up to Pontryagin. That's where we'll stop. You might say that's still pretty old because it's the 1960s. But yeah, there's only so much we can do. We can't cover more than 2 millennia in a single course, right? So, before we proceed on to something a little more technical or get our hands a little dirtier, let's think of some problems which can be fit into this. Problems that might seem very familiar to you or a little closer to your fancies. Say something such as landing a satellite on the dark side of the moon. Yes? How does that fit in with this? Okay? What is it that you're going to optimize? You're going to optimize perhaps the amount of fuel you have consumed. You might even wish to optimize, you're probably racing with a competitive nation and you want to be the first one to reach the dark side, so you're competing maybe on the time that your mission takes. You want to be the fastest one to get there, not the first one, the fastest one to get there. So even this TF minus T naught, which is the total time of your mission, might be something that you're trying to minimize. Who knows, right? So there could be several such things. What would this entail? This is some penalty that you're going to be imposing based on, suppose instead of landing on the dark side of the moon, you land on, the side that's visible to us. There should be a penalty incurred for that, right? Because your mission has kind of technically failed, even though you might say limited success and hide it under that camouflage, but it still fails, right? So this should also penalize that failure. Terminal cost is what we shall call it, right? Let's come down to earth, come down to small people like us and think that, okay, you want to win an election by spending the least amount of money in campaigns. So no flying over helicopters and visiting and attending multiple rallies within a day, perhaps saving on some cost. I don't know if anybody actually tries to set a cost function like that, but let's assume in a hypothetical world such were the case. How would you go about this? I don't really know. Don't ask me the mathematical nitty-gritties of such a cost function. I wish I could have designed it, but I don't know the answer. But the problem still sits pretty within this framework, right? As we have someone from economics, you would know that your investments on the advertisement is what you should try to minimize and get the maximum profit in return. Profit in this case in an election would translate to votes. Back in academia, if you're someone as reticent as probably me in networking, you would say, okay, I'd just like to maximize my scientific output, whether it be paper, whether it be writing textbooks, whether it be teaching and reaching out to young people such as yourselves, or whether it be, just busying myself in thinking about some problems without having to worry about, oh, do I know this guy? Is this guy going to be a favorable reviewer for me? Is this guy going to write nice things about me? I don't want to invest much time on that. So I want to minimize that sort of interaction, and yet I want to maximize my productivity. So you see, this is a very, very generic framework. And all of these cases that I've told you about, they all evolve with time. The choices that you make through this U, how many people you're going to meet, how much time you're going to do, that's your strategy. So this U is not just a control input as you see in a control system, right? This is like a strategy that you choose. In a 10-hour work day, how many hours are you going to invest on interacting with people? How many hours are you going to sit in your cabin trying to solve some mathematical problems that interest you? How do you allocate your time? And accordingly, you'll get some output. If you met the right sort of people, perhaps investing 15 minutes would have been worth it. On the other hand, if you've invested 2 hours meeting people who are not going to further your cause much, it's a waste. So that's a choice of strategy. Even that fits in with this, right? So a whole lot of a plethora of problems fit into this setting, right? We shall not have time to get into those specific nitty-gritties and applications. Needless to say, I'm not even the expert or not even the best possible person to get you into each of those specific applications. So we shall try to develop the very generic tool. Suppose you have a cost function. Suppose you know what the dynamical system is, how do you solve? How do you come up with the best possible choice of control or strategy to maximize your profit or minimize your loss? I'll just take a minute or two to be a little more philosophical on this as well. And I might say that often we have misunderstandings with people, we disagree with people. Perhaps you can diffuse the situation, perhaps you can walk out of the situation thinking it's not really a clash of two people, it's a clash of two cost functions. Why do I say that? Most often these disagreements arise because we think, how could he or she have said this? How could they have done this under these circumstances? Well, that's quite simply because of this. Because of the person that you are, because of whatever's gone into making you the person that you are, you perceive of your set of choices or your actions based on a you, a curly you, that has shaped you. And you think that the other person should also adhere to this same curly you. When the other person makes a choice that doesn't fit within your curly you, you think, how could he or she have done this and have gone off in this trajectory? You hadn't even thought about that as a possibility. You think it's unethical, you think it's wrong, you think it's morally reprehensible. But essentially that's what it is. It's not the person, it's what's been going into making that person and making that person think that certain things are part of this constraint set which are not part of your constraint control set. Right? That's what allows the person to do things which you are probably not going to allow yourself to do, and vice versa. So it's probably a disagreement, because what I'm trying to get at here is everything is at the end of the day perhaps an optimization. We might never really know what is being optimized. Yeah, in domains such as mob psychology, human psychology, it may be more intangible to actually find out what's being optimized. In physics, however, we know in many cases what's being optimized. You can call that as quote unquote the mind of God or the mind of nature or whatever you like. Light does this all the time. When? Can you tell me when light does this? Shortest path. Shortest path, is it? Shortest optical path. More like it, right? When it goes from one medium to the other, right? A ray of light refracts. There's refraction that happens. You can think of it like, okay, let's just give you a rough sketch.